Welcome to ExplainerCast, episode 13. I'm your host, Dave Smith.
And this is Shane Swenson.
And we have some explaining to do. Today, we are continuing our saga, part 5 of the Telecommunications series on how we do distant communication. Today, moving in deeper into the world of computer-to-computer network communication.
Yep. So last time we had talked about how to take multiple computers and connect them together to form a network. And we even started something simpler, which was just two computers directly communicating to each other. I think we talked about like a serial line, which is just a cable that directly connected two computers, and worked our way up through modems, and then talked about routers interconnecting multiple computers and ultimately interconnecting networks of computers, at which point we had to change the way these computers even sent messages to each other. When they were two directly connected, they just send messages one to the other. But once they're all on a network, it would be chaos to have every computer send every message to every other computer on the network. And so you need something to organize that. And we actually made a metaphor to the postal system and used the same concept, which is every time we want to communicate between two computers, they're going to format the communication into discrete messages and then put an address on every message indicating which computer on the network that message should be delivered to. And so as long as every computer on the network has a unique address, then, and all the routers know how to forward messages until they reach those destination computers, now the network could send messages from any computer to any other. And so the biggest network that we deal with in the world to this day is the internet, this global interconnected network. And that uses a set of procedures or protocols called Internet Protocol to do this. And these date back all the way to the 1980s. Internet Protocol version 4 went live in 1982, I think it was. And to this day, Internet Protocol version 4 is still the way most computers on the internet communicate with each other. They send a message, they put their assigned IPv4, Internet Protocol version 4 address in the message as the source address. They put the assigned IPv4 address of the destination computer and as the destination address. And then they send that message to their first hop, which is their local router. And then that router forwards that message based on the destination address and its routing table to the next hop, and so on and so forth, until it reaches the destination computer. And so pretty incredible that this technology itself has been powering this global network for over 40 years at this point.
Yeah. 40 years of actual application, and a lot of the protocols that we're going to talk about today were originally written about, named, and specified even before that. Even before they had the applications where they could actually run these things on computers and routers. Some really smart people were pontificating about what a future network might look like. And so a lot of this stuff was defined even before it was launched in 1982.
That's right. Yeah, the 1970s mainly, with maybe foundational work done in the 1960s. And this idea of message-based communication was a departure from the baseline networking technology of the time, which was the voice telephone. In the voice telephone, you make a connection, and there's a lot of complexity that goes into making that connection, especially over long distance. But once that connection's made, then all the communication kind of happens continuously in real time. You talk, you listen, and the signals propagate. And there were thoughts that maybe this is how you should build computer networks as well, is when a computer wants to send information to the computer, they would dial a connection, send the information, and then close the connection. But the challenge there is that you're kind of occupying a lot of the infrastructure during that time of that conversation, and you can only kind of have one of these at a time. So this idea of let's just have always on connectivity, but we'll use it on an as needed basis to communicate with any other device on the network just by sending messages to them, was a very different approach. And it had its advantages, which is it allowed a lot more kind of continuous connectivity between computers, but it did have some downsides. And one of the downsides was you no longer had this dedicated connection to make use of. You had to think about formatting any data transfer into a series of these small messages. And so I think that's what we're going to talk about today is how do you send maybe more data than fits in a single message, or how do you send maybe or have a longer conversation that has back and forth in it. And you want this to be, of course, reliable and have the appearance that these two computers are directly connected to each other, even though there's an entire intervening network in the way.
Yes. We're essentially going to describe the protocols that allow application developers to abstract away a lot of these problems, the ones you just mentioned, Shane, and a couple of others.
Yeah.
Like, for example, what if I have two programs running on my computer and they both want to talk to different programs running on a different computer? How do the programs prevent intercepting each other's messages on accident?
Right. And also, networks aren't perfect. So we have to think about what happens when a message is lost, or it may be dropped intentionally because the router didn't have capacity to deliver it in a timely fashion.
Mm-hmm.
Well, also, it turns out networks will sometimes duplicate messages. They'll actually make copies because maybe they felt like they needed to resend it, and now both copies are transmitted through the network. And also,
yes.
If we send a sequence of messages, it's very possible that they'll arrive out of order for various reasons.
Right.
Maybe some had to be retried, or they took different pathways through the network. And so
yes.
It's kind of a free-for-all in a way.
Yes. And there is another source of errors that you didn't mention is, what if some of the bits in your message get accidentally flipped on the way?
Yeah.
By a mistake, and
Yep.
this can happen for a lot of reasons: electromagnetic interference, cosmic rays, literally.
Yep.
And this can happen. How do we know that has happened on the other end and fix it?
Exactly. Yeah, so across all these kind of different service errors and this message-oriented delivery service itself, which is often referred to as a best effort service, meaning the network's not guaranteeing it's reliable. The network really is designed to do the best it can do with the conditions at the time. We're going to talk now about how do we make something that has at least the appearance of being reliable.
Yeah.
And dealing with and fixing up all of these errors.
One way I like to think about this is that on average, the network is reliable.
Yep.
To a measurable degree. Call it 99.99% of all packets sent over the internet protocol will be delivered intact, in order, no errors, and no problem.
Sure.
But because of that 0.1%, 0.01%, whatever it is, it's a made-up number, every single application developer would have to build all of the code to handle these things, were it not for a nice invention called, should I just name it?
Go
Shane?
for it. Yes. We've teased enough.
It's a nice invention called TCP, or Transmission Control Protocol, which is implemented now in every operating system pretty much on Earth that connects to the internet will have a TCP feature.
Yep.
So that developers can build applications on their computers that don't need to solve or resolve all of these same problems. They can just rely on the operating system to take care of them for you.
Exactly. And so as a software developer, we like the network because it gives us connectivity and we can create much richer applications that way. But I'd say most software developers sort of hold the network at arm's length, and they honestly wish that it just was perfect, that it was instantaneous delivery, perfect reliability, infinite bandwidth. And we can't actually, physics doesn't let us do those things, but TCP lets you get way closer to the feeling, at least, of that infinite perfect reliability than you could get without it.
Yes, for sure.
So TCP, the history on this goes back again to the 1970s, when computer science researchers and the pioneers of the ARPANET, which became the internet over time, were just working on the different ways to connect computers and to have them work together. And so Vinton Cerf and Robert Kahn were two of these researchers, and they had this idea that, great, we have a network, it can send messages between computers on the network, but we need all these reliability features. And so they defined the TCP, the Transmission Control Protocol. And actually, I think initially they thought that was going to be the whole internet protocol as well. And it was maybe a later revision of their work where they realized the need and benefit would be to split into these two protocols and what we kind of think of as two layers in a protocol stack, where the internet protocol layer is focused on individual message delivery. And then TCP makes use of that service, which is the ability to deliver messages one at a time from one computer to another, and adds all the reliability and some other functions called flow control to ensure that the network and the end computer can actually handle the data you're sending to them. And so over time, what's now happening is TCP has gone through a number of small changes, but it's still fundamentally the same protocol as it was in the 1980s. And meanwhile, the internet protocol that underpins it is being upgraded from Internet Protocol version 4 to Internet Protocol version 6, and TCP can still work, in part because it's a separate layer. And then as we talk about the details on TCP, we'll actually find that some of its features are not only needing to be optional, but they're actually problematic for certain applications. And so this was another benefit of the way they separated the layers, is it turns out there are some alternatives to TCP as well for the cases that you don't want to pay the penalty or the price needed to gain the reliability that it offers.
Yes. It's very, very cool. And how do you visualize these two protocols? You know, I think of it like IP is carrying the TCP content, and then TCP is carrying the actual data that the application is trying to send. Is that the right way to think of it in the form of nesting?
Exactly. Yep. Yeah. So if you think about our application, maybe we want to download the content for a web page or send an email. And so the application is defining that data, that content, and then TCP's job will be to take that data to be transferred and to potentially divide it into multiple individual messages, and then format each of those individual messages into the Internet Protocol structure, and then using Internet Protocol, ask the network to transfer that message to the receiving computer, where they'll then extract the TCP payload back out, perform the TCP functions, and ultimately put back together the original data stream that needs to be delivered to the application, like the web browser or the email client.
Yeah, maybe we could spend some time talking about the sequencing of messages like that you just talked about, putting the stream back together in the order that the original sender sent it, so that by the time it arrives at the destination, it's in the same order. You want to, should we dive into that a bit?
Yeah. So now I guess we should just, let's start talking about kind of the fundamentals for how TCP does this job. And so TCP, I'd say, really has a few basic functions. One of them is, I'll call it session management. And so let's come back to that one. And a second function is going to be flow control. We'll come back to that one later. But here, what we're going to talk about is we're going to talk about like in order information delivery and reassembly. And so the challenge is that if we have a large document or a large amount of data to send, we can't just format it as a single IP message. And there's a few reasons for this. Networks will have what's called an MTU, a maximum transmission unit, which is the largest message they're willing to transmit. Typically over each hop, there'll be a separate MTU. And this ends up being really important. Few reasons. First one is, if I'm allowed to send an infinitely long message, I'm going to consume all of the capacity of the link for all the time that I'm using to send that message, and I'm going to starve everyone else from using that link. And so that's called head of line blocking. And so MTUs say you can only transmit for the maximum size of the message, and then you have to stop and give someone else a turn. So there's a fairness aspect to it. Another is, even at the point-to-point interconnection level, and also we'll find out at the TCP end-to-end messaging level, if we have errors in the message, we'll typically send a duplicate copy of the message and hope that that one is received correctly as a way to overcome those errors. So the larger the message, the more likely an error is to be in that message if there's kind of a constant percentage probability of any given bit being an error. But also, the more data we have to retransmit every time an error takes place. So it kind of hurts you twice to have really large messages. If they're big enough, they're always going to have errors, and you're going to always have to retransmit them on a noisy network. So that's kind of a second reason to keep the MTU smaller. A third reason is for both message management and for things like retransmissions, every forwarding device or every computer that's going to be, or router that's going to participate in this, needs to have enough memory to hold the entire message in a buffer while it processes it. And so the MTU also establishes the largest message you need to have buffer memory for. So for all these reasons, again, think like a postcard, as we talked about last time, there's a fixed maximum size for your message.
So Shane, do these routers or these devices that are in between the computers relaying messages, do they advertise their MTU size, or do they just cut messages up without the sender or receiver knowing it happened?
So that would vary based on the protocol. I think there are some what we call link layer protocols. These are lower level point-to-point connectivity mechanisms that, like, when two routers connect to each other, they'll negotiate some parameters, and sometimes the MTU is just defined by the protocol they're using, and in some cases they can negotiate to change it. And so there'll be sometimes a default, and then again it could be larger. And then the challenge for TCP, though, is you actually care about the MTU, the maximum transmission unit, the minimum of all those values along the path between the two communicating hosts. And so there isn't a straightforward way to ask what's the maximum transmission unit on this entire path.
Yeah, because you're not even allowed to know what the path is, who those hosts are.
Right. If the path is consistent, which it often is over at least a short period of time, then you can perform what's called path MTU discovery, where you basically just send larger and larger messages and see which ones get through. And the routers in Internet Protocol do have the option, if you send a message that's larger than they're able to forward, they can reply back with an error message that says, this message was too large, MTU exceeded, or something like that. But a lot of times they'll just drop it on the floor or just delete it, essentially not forward it. And so you have to tell, like, my messages aren't getting through. I guess that's too big. I'll try a smaller MTU.
Okay, got it.
So anyway, that's the MTU thing. And so that's one of the motivations for why we even have this sequencing problem, where any message larger than the MTU of our path has to be divided into small messages. And if you want to rule of thumb...
And does that dividing up into smaller messages, does that have to happen at the sender?
Yes, it does. So, well, yes, with a caveat, like everything. There's always an exception.
Yeah.
So, yes, it does. However, the original Internet Protocol specification did allow for the possibility that maybe somewhere down the line you encounter a network with a smaller MTU than what you were anticipating when TCP first subdivided the message. And so there was a concept in IP called fragmentation, where an IP router that received a message larger than it was able to forward had the option to take that message and divide it into smaller IP messages called fragments, forward each of those, and then they'd be reassembled somewhere on the receiving side. That maybe used to be more common. I don't think it's super commonly exercised at this point because it's more resource intensive in the router. And so modern routers tend to just drop large MTU packets rather than fragmenting. And most end computing hosts now either just assume a smaller MTU and so they work fine, or they do an MTU discovery process to kind of optimize it.
Right. Okay. Makes sense.
And to think about MTU, just to give it an order of magnitude, the ubiquitous local area network protocol called Ethernet set a maximum size of roughly 1,500 bytes. And that ended up kind of becoming the de facto MTU for networks globally as well. And then at the TCP layer, you have to assume that some additional protocols are going to add information to this message before it actually hits the wire. And so they'll back off from that. And so they might set, put 1400 or 1200 or 1100, ish bytes of data into each message so that as it accumulates some headers, it still fits in that 1500 byte MTU when it hits an Ethernet segment.
Okay.
So now we've motivated it. So what are we going to do? And again, I guess picture yourself, Dave, if you had you had a long speech that you wanted to write and you were going to send it, and all you had available to you were postcards, and you needed to send the speech across the country. What would you do?
Yeah. So, I mean, the first thing I would do is I put a number on each one,
Exactly.
like a page number.
Yep.
So that's the first one. And then I would also need to probably design a process so that if the recipient is missing a number, they can tell me, hey, I didn't get page 7.
Yep. Yep. Exactly.
And they could also tell me, well, then I could just resend page 7, right? I could resend it. I have to rewrite that page.
Yeah. And so if you're
And then
TCP,
send
you'll
it
save
again.
a copy so that you can just send them a new copy, because you'd hate to have to remember what you wrote from scratch.
Yep.
Yeah. So, and that's basically it. There's just a couple tweaks that are in, because we're dealing with computers and we don't actually know the size of each TCP
Mm-hmm.
data segment. And so TCP will use sequence numbers on every message, but the sequence number is actually going to be a byte count. So rather than a page count, which is what we human beings think about whenever we write something like this, it's actually going to count essentially the characters, but very specifically, it's the bytes in the sequence. And
So in the postcard example, for let's say my first postcard has 100 words on it.
Yep.
And each word is like 5 letters long. We would say something like, okay, this represents up to character number 500 in my total paper. And you'd write a 500 on the first postcard. Is that how that would work?
so you would write the
Or would it
starting,
be a 0?
you'd write a 0 on the first one. Well, actually, even that, there's a caveat too, which is because if you always start at 0, then it makes it easy to guess the sequence numbers and you can perform attacks against TCP. TCP will actually start by generating a random sequence number to start at. And
Yes. To prevent someone from inserting their own words into my my paper.
Exactly. Yeah. And so so actually at the very beginning, I'm going to talk about session management, I guess, briefly. The very first thing you would do, and the same thing would happen when you're going to send this message to your friend across the country, you're going to actually send them some messages just to initiate the conversation before you send them any of the data. And so in TCP, the first message you send is called a synchronize or a SYN message. It has a flag marked that says I'm sending you this initial message with the SYN, the SYN flag. And I'm going to provide a mostly randomized initial sequence number. And so this is going to represent 0 essentially, or like the start of my message is going to have this sequence number on it when I actually get around to sending you some data. And then the receiving side, if they're willing to make a connection, they're going to respond back with an acknowledgement and a synchronize of their own, one message called a SYN-ACK message that has their initially chosen sequence number for any data they send back to us. And they're going to acknowledge that they saw our sequence number and they are waiting for that first piece of data. And
do they send back a copy of the sequence number in the SYN-ACK?
Yes, exactly. So what they acknowledge, and then so this is the detail that we'll get to, is then going forward, we're gonna acknowledge their sequence number, and then we're gonna start sending data, and then it'll become more clear. When we send data, we're going to send in that message the sequence number of the start of the data in this message. And so initially it's gonna, I think it's gonna match our initially chosen sequence number and essentially say, okay, here's the start of what you should be expecting. And then there's, I think, a length field in the header. And so, if it started at, number 100 and it was of length 500, that you just received essentially, 100 through 599. And then you're going to acknowledge back to say, I am expecting starting now, I'm expecting sequence number 600 because that's the next thing I'm expecting. And so the way you acknowledge is you sort of acknowledge everything you've received up to that point, by saying what you expect to see next.
Right. And that tells the sender, hey, I've received all your postcards up to this character number.
Yep.
So please continue. And if you have that tells me as the sender, it tells me something really important, which is I know, like, let's say they acknowledge up to character 10,000 of my writing.
Yep.
But I know I've sent up to 12,000.
Mm-hmm.
So if they tell me 10,000 and I never get a 12,000 acknowledgement, that tells me something.
Exactly.
That somehow one of my messages was lost and I need to resend it.
Exactly. Yep. That's exactly right. And so the tricky bit with this is it's really hard to properly say a negative. It's hard to say what I don't have because I don't know if I'm supposed to have it.
Yeah, exactly, because you don't know.
Yeah. So I tell you what I know, which is that I got up to this point, and then the sender knows what they've sent. And so then maybe on a timer, they say, well, it's been long enough.
Yep.
I should have received an acknowledgement for this yet, and I haven't. I'm going to send another copy starting at that next sequence number that the receiver is expecting.
And this is probably one of the points that TCP gets criticized for the most, is because there is no mechanism, and maybe there can't be for this exact situation, but there is no mechanism for the receiver to say, hey, really, this message has been dropped. You need to resend it now. Instead, the sender just has to wait. And if as soon as they feel like they've waited long enough, then they can do a retransmit.
Right.
And so TCP is criticized sometimes for being slow or low performance in the face of these kinds of errors on the network.
Yeah. It's a tricky thing to get right. And I think there is maybe a mechanism that's probably optional, like a lot of things, where if the last thing I've ever received was like you said up to 10,000 or something like that, like I don't honestly know if I should have received anything after that. So I don't know what I would acknowledge or ask for more of. On the other hand, if you start to receive additional messages with larger sequence numbers, but there's a gap, like you're still waiting for 10,001.
Yes, now you know. Yeah.
And I think in that case, you can send back an acknowledgement that is a reminder, I'm still waiting for 10,000 or still waiting for 10,001, however it is. And so that can be like a clue to the sender. Wait a minute, I'm getting these duplicate acknowledgements. Maybe that means they're actually receiving these other messages I sent later in the stream, but they're missing this one in the middle. I better resend that one. And so there can be a way to kind of close the gap faster that way.
Yeah, and then I want to go back just a little bit here, Shane, just to point out something in case it wasn't clear, which is that in the same way that the IP or Internet Protocol packet structure has both the data that the sender wants to send and some metadata about it, we call those fields headers, and we've used that term here as well.
Yeah.
And I think it's just worth reiterating that all of these messages have special designated headers that are included in every single TCP message. And we've just talked about a bunch of them, the synchronization field that says it's a synchronization, the sequence number, the acknowledgement number. These are all special fields that every single TCP message must carry to carry out its job of doing everything we've talked about. And that's in addition to the data. And so that's what we mean when we say header.
Exactly. Yep. And we call it a header because it typically goes kind of in front of the body or the data that is being carried in that message, just in the way that it's laid out. Okay, so
all right.
So a couple more things. So if there's a gap, we're going to keep acknowledging what we're waiting for until the gap is filled in. That's good news. If we receive messages out of order on the receive side, we can use their sequence numbers to put them back into the right order. So we solved for that one. We mentioned bit errors. So TCP does have a checksum, which is, again, a unique computed code that uses some math essentially to say if you compute this arithmetic function over the data, you should get this answer. And if you get a different answer, it probably means it does mean there's an error somewhere in the data. And so this message is invalid. You should drop it. And again, it needs to be retransmitted. So what else did we talk about that we need to cover?
Well, there is more that we'll get to later, but I think we've done pretty good. Maybe we need to talk about the finalization of an inter communication between two TCP agents. Like, how do I know as a receiver that I've got the last message, and so now I can tell the application that's waiting for this information, hey, here's your complete message from 0 to whatever, 80,000 bytes. Here's everything all in one unit in order. I promise it's all in order.
Yeah.
How do I know that I've got the last one?
Yeah, that's a good question, and it's actually a tricky problem. If you assume a network that is unreliable in the worst possible ways, it actually is really hard to tell to definitively know when you're done. Because, for example, what if the network just consumes the "I'm done" message, for example? And so, also in some cases in TCP communications, there isn't necessarily an end. Like maybe you're just sending frames of a streaming, security camera video or something like that forever. And so you're kind of never done in some cases, but in other cases there is a very defined done. And so when you hit that point, then TCP does provide a mechanism. There's a fin or finish flag that you can set. And when you set that flag and send that message across, that says, I've sent everything I intend to send. And then the recipient will usually send back a fin ACK flag that says, okay, I've sent everything. I acknowledge you, and I'm sending back everything that I intend to send. And now there's this open question, which is, do you acknowledge that, even though you said you had nothing more to send? And is the other guy even listening when you send the acknowledgement? So there's kind of this awkwardness around hanging up, but TCP does have a sequence.
It's a perfectly modeled after human awkwardness. I never know when to actually hang up the phone. It's like, I've said goodbye, you've said goodbye. It's like, do I wait? Do I say goodbye and hang up? Do I wait for you to say goodbye back to me? I don't know. TCP has the same problem.
Yeah, somebody has to go last, and it's hard to know who it should be.
And then there's also, so actually one quick thing on that, you've mentioned the word flag a few times. A flag is really just a bit. It's a single 1 or 0 in a special reserved position within the TCP header that is for that purpose. And so the fin bit is one specific bit. I don't know, it's like bit number 100 and something in the top of the TCP message that's allocated. And so anytime a receiver receives a message and it sees that bit is a 1, it means something. It means that, oh, I'm done. This is a fin or a finish message, and there's like 6 or 8 of these things.
Yeah, exactly. Yeah, these flags are really just used again by TCP to coordinate certain details, and then they have these other, call it, fields in the header that contain more information, like those sequence numbers, for example, and the checksums.
And then, Shane, I wanted to ask you about this part. It's been years since I've studied the flags carefully, but there's also, in addition to the fin flag, there's also a flag called RST, or reset.
Yes.
What is the difference?
So I think of reset as the unceremonious, like slamming the phone onto the hook, and ending the call right now kind of flag.
Possibly mid-conversation, like, oh, I have more to send, but the receiver said reset.
Tough. Yeah, exactly. Yeah, and so I can't remember the history of why like reset is there versus the fin, but it essentially is the hard stop. And so if a TCP implementation receives a reset that is valid, which means it's associated with a sequence number that's in the right range, because this is another form of attack people use, is, hey, can I like interrupt your conversation by just like flooding you with a reset that you didn't expect. But if they receive the reset, they essentially like, okay, that one's done. I'm not listening any longer. And there are some other things, like sometimes messages take a long time to reach their destination. Maybe they're stuck in some buffer somewhere and then they suddenly get resent later. And so TCP kind of has these holdover time windows where it won't expect more messages, but it's possible that some are going to show up. And I don't know if the behavior of those is different with a fin terminated conversation or session versus a reset terminated session.
Well, now I got to tell a really fun story about reset.
Okay.
That goes back a few years. Is it okay?
Yeah, please.
You mentioned that you can do a reset flood and you can stop people from communicating on the network by just injecting these packets that say reset.
Yep.
And that tells the applications or the operating systems, nope, sorry, we're not going to get any more content here. Well, back in the early days of Wi-Fi, before encryption was ubiquitous, or if you had a hub, an Ethernet hub instead of a switch, when every single connected node on the hub could see all the traffic for all the other connected nodes, you could do things like this, and it was really fun. And I'll just give one quick example. A friend of mine and I found that you could inject responses to TCP messages that were not intended for you by spoofing the source and destination IP address, and then you could change the flag, the sets of flags to whatever you wanted. And so if you saw, for example, a web browser requesting an image from a web server, you could insert a reset packet to send to the web server as if to simulate the browser saying, oh, you know what, never mind, I don't want you to send that back.
Oh, yeah.
Then you could send your own TCP responses to the web browser with your own image content. And this, boy, you could just have a lot of fun with that. You could take, because you stopped the original server from serving back the image to the browser, you could just inject your own image. And one of the things we did that was really fun was we would actually ourselves go and we would record the URL of the image that the original browser requested. We would then go fetch that from the web server. Then we would flip it upside down using a little program that was running on our local computer. And then we would serve the upside down bytes back to the original browser. So everything that they saw on the internet, every picture was upside down.
Oh my goodness.
It was so fun.
That's awesome.
And we weren't the ones that came up with this. We just built it after seeing it. But I think someone called that the upside down internet, which I just thought was awesome.
That's pretty awesome.
Yeah. This has become almost impossible to do today, but boy, was it fun 20 plus years ago.
Yeah. Yeah. It's crazy how just really these protocols are pretty simple and straightforward when you come to understand them. And in the 1980s, 1990s, even early 2000s versions and embodiments of them, there was very little protection or security. It was just trust everywhere. It was like where I grew up, and you always left your door unlocked. You left the keys in the car. It was just kind of pure trust. And that's how the internet was up until, realistically, the last 20 years, it's been all of the changes. And so
mid-early 2000s even, I would say, there was unencrypted Wi-Fi everywhere.
Yep.
There were Ethernet hubs everywhere. So it was probably until like 2005, 6, or 7 before that stuff became ubiquitous, the security stuff that prevent this kind of shenanigans.
Yeah, that makes sense. Yeah, and so at the time, just good innocent fun, but of course those same mechanisms can be used for more nefarious purposes. And so things like encryption help. And then, for example, for like a reset attack, this is part of, again, why the sequence numbers are initiated somewhat randomly, is to try to reduce the danger of a successful injection attack. And for example, if a TCP implementation receives like a reset, but the sequence number associated with it is outside of a pretty narrow range of what they're expecting right now, they'll just ignore it. And so that gives them kind of a statistical filter is one way they do it.
And those algorithms are implemented by operating systems for exactly this purpose, to try to stave off attackers like this. But I remember back in the day when we were doing this, every sequence number we ever saw started at 0. It was not a problem.
I believe it. I mean, that's how I would have coded it until someone pointed out why it mattered. And then, of course, you change it.
Yep.
Yeah.
And now I'm sure they're all randomized. In fact, I think I remember when the Linux kernel got a patch to randomize TCP sequence numbers. I think I remember that was an interesting day in the world of networking.
Yeah. There were probably, and you think about something like that, there were almost certainly TCP implementations out at that time that didn't deal well with non-zero starting numbers because they'd never seen them. And so even if the spec says you should handle it, it doesn't necessarily mean everyone's going to follow that if they've never seen it in their testing.
Oh, yeah, for sure. In fact, it's very easy to build a super low performance, super naive TCP implementation. And I know this because I did build one in college.
Nice.
And I found that you could be very lazy with your TCP implementation and it would work even though it would be very, very slow.
Yeah.
Like, for example, if you're on the receiving end and you get packets out of order, well, there's two ways to handle that. You can either take the out of order packet and save it off in a buffer for future reference when all the other packets come in, or you can simply ignore all packets that are out of order until the client eventually resends them in the correct order. And it's way slower, but it does work.
Yeah, that makes complete sense. Because in your case where you just drop them, when you finally got the missing packet, you're just going to acknowledge that packet's data, and then you're going to get even though you had previously received a copy of the one that follows, you're going to get another copy of it. A modern implementation, if you actually buffered all that up, when you receive the packet that fills the gap, you don't acknowledge that packet. You acknowledge that packet plus everything continuous after it. And so your acknowledgement tells the sender, oh, I caught up to this point here. But yours didn't have to do that for sure.
Nope. And that was enough to get me the A in my CS 460 networking class.
Nice. And that could have probably gotten you a PhD in, 1975 too.
Yeah, amazing. Amazing what 30 years does
Yeah.
to the PhD.
To undergrad trajectory, yeah.
Yeah, what was state of the art is now like a junior level class.
Yep. Yeah, exactly. So let's talk about a couple other things that TCP does. One of them, another way in which it gets blamed for making things slow, is that TCP is also responsible for what's called flow control. And this is another problem you don't think about until you see it. And that is that when I have a lot of data to send, I have to know how much memory do you and your your own homebrew TCP stack that you wrote yourself, how much memory do you have that's available to receive data that I send you? I can't just send you all that I have at the same time and expect you to receive it all. And I also need to know how much capacity is there on the network between me and you that I can send into. And so the way that this happens is the receiver will also, when they acknowledge back to the sender, they'll also advertise what's called a window, which is to say, I have enough memory available for you to send up to this much data and I'll be able to handle it. But don't send any more than that until I start to acknowledge some of it. And so this empowers TCP to then send up to that window size, which might be multiple messages, multiple MTUs worth of data. And because that's all being sent at the same time, that allows you to send essentially more data faster than if you sent one segment and then wait for an acknowledgement, send the next segment, wait for an acknowledgement.
Exactly. And I think that the postcard example is a good way to understand the huge amount of delay that would introduce if you didn't have a window like this.
Yeah.
So imagine if I had to put a postcard in the mail with my first 500 words.
Yep.
And then wait for the person on the other end to receive that postcard and then send me back a postcard that says, I got up to 500. And then I'm like, okay, great. Now I'll send you 500 through 1000.
Yep.
And it's like 4 or 5 days between each one. But what if I could send like 10 postcards all at once?
Yep.
in the mailbox, and then all at once the person on the other end can acknowledge, hey, I've gotten 10,000 characters worth of your paper now, and I'm like, great, now I know I can send another batch of 10.
Exactly. Yeah. So you can't make the propagation delay, the latency, any lower, any faster, but you can.
Right. That's physics.
Exactly.
Usually.
But, yeah, physics and maybe the construct of the machines. But yeah, you can definitely
physics and a little bit of budget.
That's right. There's some dollars there. But yeah, you can get more bandwidth, we call it, or just more total transfer capacity in those round trips by sending multiple messages. And you described it as a bundle, but you could also, essentially say, well, every minute I put a new postcard in the mailbox, and sure, in our case they get bundled, but fundamentally they could all be transferred on their own, kind of like, I don't know, like, pick your metaphor, like individual elements all traversing kind of in a convoy, but each kind of with their own, they're each being routed by the router separately. They're taking probably the same path for efficiency, but not necessarily by design. And then they're each being acknowledged as they're received. So there is one other constraint that flow control needs to take into consideration, and that is the network itself. And so what if you as a recipient advertise a huge window, you can receive tons of data, but the network between us is very low capacity, and we could overwhelm some of those routers on the network itself. And so TCP also was designed to try and not overwhelm the network too badly by essentially send a certain amount of data, wait for acknowledgement, and as you receive acknowledgement, successfully send a little bit more data on each round trip and sort of build up the size of that window that you're willing to send. And the signal to slow back down would actually be when the network couldn't handle that quantity of data and started dropping some of the messages.
Yes.
And at that point, TCP would then say, I need to slow way down. And so it would back off. It'd usually divide that total window in half and say, I'm going to try sending half this amount of data and then start growing it over time. And so if you watched what sort of the internal statistics of TCP, you would see they kind of like have this sawtooth oscillation where I'm sending them higher and higher rates. Oh, I hit some congestion. I sent too much. I then scale down. to a smaller amount, and then I start working my way back up again. And the goal was to
And is this what's called the TCP slow start algorithm?
Yeah. So there was
this?
kind of three things. There was slow start was actually at the beginning. Is ironic. It's not a slow start at all. Like the way slow start worked was like on every message that is successfully makes the round trip, I send 2 messages out basically. So it's actually like exponential fast start, even though they call it slow start. But I guess you started
it does have
slow.
some amount of ramp, I guess.
Yeah, and you started at a small number, so maybe that's what they meant by slow start, but you didn't stay slow. And then post kind of that, when you started to hit congestion, then it switched to this more linear mode where you kind of try to increase linearly, but then you decrease exponentially, like by half. And this is what preserves kind of the dynamic stability of the network, that you back off faster than you grow, and that way you don't keep like overwhelming the network over and over again. It's also what in theory lets multiple different computers on the same network sort of fairly share the network, because reality is congestion or overutilization of the network is a shared problem. And
yes,
and so there's an incentive to, in a tragedy of the commons, if I just try to maximize my own throughput to the detriment of everyone else, and then they try to do the same thing, we're all just gonna congest the network. And then
the network won't really be able to deliver anything,
right?
Not mine or yours.
Exactly, and we'll all just be stuck waiting.
It is really
line.
cool because this algorithm where it detects congestion and then backs off on the send speed. It's not constant. You might think, oh, great, I'll do that once and determine the speed of this network, and then I'll just send at that speed. But it's not the case. Instead, TCP has to constantly be monitoring that and always be vigilant in case it needs to drop the speed at any moment. Yep. Because, for example, another application on the same network just happens to pop up, and you're running at full saturation of the network. Maybe you're getting 100 megabits per second or something, and then someone else comes on that same network, and suddenly now you're only getting 50.
Yeah.
Well, that's because of this TCP congestion control logic.
Exactly.
And that kind of, Shane, I think that kind of reinforces the point that both of these protocols we've been talking about, TCP and IP, which carries it, both of these are not just definitions of what bits go where in a packet. They are also accompanying behavioral specifications that say computers who participate on this network must implement certain logic to honor the information that's in these packets.
That's right. Yeah, and this was a super important innovation, and there was a lot of research and experimentation and optimization done around congestion control, because if you do it badly, you end up with bad outcomes. You either end up overusing the network and it's bad for everybody, or you end up being too conservative and underutilizing the network, and then you're not getting what you paid for and what you built. Mm-hmm. And so it's like, how do you fairly share a limited resource on demand in real time? And so it's pretty intricate and pretty amazing, and people are still kind of tweaking it to try to get better performance out of it. But again, it's a fundamentally a shared distributed challenge, and again, TCP is essential to doing that in this system.
Okay, well, at the beginning of the show, we listed like 8 different problems that IP didn't solve.
Yep.
And TCP attempts to solve for us. Do you think we covered all of them? Are we missing anything?
So I think we covered most of the reliability attributes. We talked about, so if I get a duplicate, well, it's going to have the same sequence number, something I already saw, so I'm just going to drop it. If I'm missing something, I'm going to wait for a retry, or maybe use that duplicate acknowledgement trick to force a retransmission. I have a checksum to check for errors. I'll drop messages and pretend they never happened if that occurs, and then do the retransmission. And then the other thing that, and we talked about congestion control and windowing. One other thing we did mention is that IP's service definition was to send a message from one computer to another. Yes. But on that computer, we have multiple applications running that are all using the network. And even those applications might have multiple sessions or conversations that they're part of. And so TCP also provides a mechanism for application level session management. Do you want to introduce what that is, Dave?
Yeah, so if I've got 2 programs, like let's say I'm listening, I've got my Spotify up and I've got my Chrome web browser up on my computer at the same time.
Yep.
All of the IP packets that are flowing to my computer from Spotify and from the websites that I'm browsing, they're all going to the same IP address. It's my computer's IP address.
Yep.
But the operating system needs to know some of these packets are meant for my Spotify application, and some of them are meant for Chrome. And it does that through a feature of TCP called ports.
Exactly.
And a port is simply a number that is part of the TCP header. It's a 16-bit number.
Yep.
And there is a source port and a destination port. And the way that works is when I open up my Spotify client and it goes to talk to the Spotify servers, it will establish a TCP connection to a known port on the Spotify servers. I'm like 90% confident it's going to be port number 443.
That's right.
But it will generate a random, not in use port on my computer that's usually a very big number. It's usually, very big. Compared to 443, it's very big. But it's like a 5-digit number, like something in the
upper end of the
1,000 to 65,000 range, approximately.
Yeah. Yep.
Yeah, and it'll be up in the upper end. And the operating system is responsible for keeping track of which ports are being used by which applications, so that when these packets come back over IP, it can look inside the TCP header and say, source port number 43582. That is for Spotify. I'm going to send this TCP message to the Spotify application. Port number 38497. That's for Chrome. I'm going to send that to Chrome.
Yep.
And so you actually have a little mini router running inside your operating system, routing TCP messages to applications. So instead of routing it over like a network, it's routing it over just between processes on your computer.
Exactly. Yep. And I do this all the time. You made one tiny misstatement, and that is when I send the message out, I put that randomly selected source port on. When the response comes back to me, the port that I selected that was the source port will actually be the destination port. And so when I receive it, I look at that destination port and I look it up in my table and I say, here's the correct sequence and memory buffer, and here's the correct application to give it to.
That's right.
On the server side, when they received that message from me, or from you in your example, they will have looked at the source IP address, which is going to point at your computer that sent the message, and they'll look at the source port, and that's how they'll keep track of which session that message is a part of. Because the destination IP address is going to be the server's IP address, and the destination port is going to be that well-known port 443 in the case of secure web traffic. So it's only going to be the unique values from the client that initiated that connection that'll make that session identifiable to the server. So
exactly,
the set of values, the source and destination IP addresses, and the source and destination ports, and then the protocol that we're using, TCP, those 5 values are called a 5-tuple, and those represent a unique end-to-end, application-to-application conversation on the network. And every separate TCP session on the network is going to have at least one difference somewhere in that 5-tuple that makes it unique from all the other 5-tuples active on the internet right now.
That's right. And your computer is keeping track of many, many of these at any given moment. I mean, right now, we're on a Zoom call. I've got a Chrome browser open with like 20 tabs.
Yep.
I got Spotify open, and so the operating system on my computer is just diligently accounting for all of these things.
Yep.
And the servers that it's talking to are doing the same thing. And one thing, Shane, that I think is really cool that TCP enables is it actually allows this bidirectional flow of information. So far, all the examples we've shared are They seem unidirectional, like I'm going to send you a paper composed of postcards, but you can just as well be sending me back data over this same 5-tuple session, but all of the ports and IP addresses are reversed.
Yep, exactly. Yeah.
Your destination is my source and vice versa.
That's right. And so, this level is where it really turns into that two-way, what we would call full duplex, meaning we're sending and receiving information, at will, conversation or session between two end hosts over a network that is really all based around give me a message with a destination address on it and I'll try to get it there. And the idea of sessions and two-way and all that is not really in the network. It's only in these two end hosts. And
by the way, these port numbers also had to be randomized for the same kind of security reasons that sequence numbers were randomized.
Yep. Exactly. Yeah, because if you can guess, like, I know you're going to be on port X, well, then it makes that injection attack you described just that much simpler.
All right. Well, Shane, we've covered a lot of ground. TCP is it's a marvel, in my opinion, of modern technology. Yeah, it's got some drawbacks, but by and large, TCP has probably been along with its companion IP, one of the most successful protocols, most widely implemented protocols in human history.
Yeah. And I think, I mean, really, as I think about it from an engineering standpoint, I think it really needs a lot of credit for the sort of taming of the chaos that was invited
Yes.
by building a purely message-oriented network as opposed to a connection-oriented network like the telephone network. And
Right.
and TCP is kind of what brought that back into like, okay, yes, computers can talk to computers, they can establish a connection. We know how to think about that. And not for all, but for many application developers, that's what you want is connect to that
Yep.
server, send it some information, receive some information, maybe back and forth some more times, hang up. Like that's the kind of the call model people have in their head. And TCP does enable that.
Yeah.
But
and how remarkable that the inventors were able to anticipate the needs of computers running multiple applications that each need their own sessions in a world where they didn't even have time. I mean, they had timeshare mainframes back then. You know, it's like you couldn't even barely find a personal computer that could even implement applications where you could run more than one application at once.
Yeah, though side story on that, I've often wondered this. I think we human beings we invent and we forget, we invent and we forget. And my personal experience with this was, so I grew up, I had a DOS PC, and it could do one thing at a time. And so I thought that's what a computer was. And so it blew my mind the first time I saw Linux running on a PC, and the fact that you could have like 6 different sessions running at the same time using like keyboard shortcuts. And it just blew my mind. Wait a minute, a computer can do more than one thing at a time? And it turns out like that story's happened so many times. So big computers, mainframes, started as one at a time, single-threaded, single process. And then they got into multi-user and what was called time sharing. And there was an operating system project called Multics. And that was a multi-user time sharing system where the computer could do lots of tasks at the same time. And I didn't know this until relatively recently, but the operating system Unix was actually defined as, we're going to make a simpler thing. Multics is too complicated. We're going to make a simple operating system that only does one thing at a time. And the name Unix was like a joke against Multics to be like, we only do one thing at a time.
Even though it was never intended to do one thing at a time.
I think initially it might have been. And then...
Are you serious?
I think so.
No way.
And so here's what this makes me crazy is, so then the original like TCP, I don't think had ports in it, like in the 1974 version.
Oh, really?
I don't think
that was
so.
a later invention.
I think it was added later when they're like, oh, wait a minute, like these like multi-user time sharing.
Honestly, that would make more sense because the foresight that would be required to build it the way that it ended up would be just impossible. It's like I would accuse you of having a time travel machine.
Yeah, it's hard to anticipate all these things. And so then, the PC went from, single process to multi-process. And then when mobile devices like your smartphones first came out, I don't know if you remember, like iPhones before like the 3 or so could only do one thing at a time. And then eventually it was really cool. They could do like background app refresh. And of course now they're just full multi-processing machines.
Right. They're more powerful than any machine I've owned prior to 15 years ago, probably.
Exactly. So the idea that we want to do multiple things at a time did evolve, but beautifully the protocols were able to be changed in time, that's the formulation that we live with. And so again, going back again for, all the way to the early 1980s, the construct of these protocols really hasn't changed that much. And I do think that's remarkable engineering. Now, let's take just a minute and I guess point out some of the negatives, because there are alternatives and they're important. So can you think of what are the like biggest downsides to using TCP, and what cost is it incurring to us?
I mean, the one downside I'm aware of, I mentioned earlier, which is the retry requires a timeout. And so that means in the face of errors in the network, you have non-optimal performance.
Yep. Yeah, exactly. And this is a big one. And part of the TCP service model was really specific, which was that it categorically refuses to deliver out of order information or information with gaps in it up to the application. It's just not allowed to do it. And so there are certain applications for which this is a big problem. And mainly anything that has a real-time interaction component that's latency sensitive, like this video or this voice call that you and I are having, if I had to wait for TCP to retransmit what you said a second ago before I get to hear what you just said, the conversation gets pretty awkward whenever we lose data.
Right.
And so what I would prefer would be, forget about the past, just keep giving me the up-to-date information.
TCP is bad for applications that not only need real-time information, but also for whom timely, recent information is valuable and past information is not.
Exactly.
So like real-time communications like video calls and video gaming are
big one.
two great examples of this.
Yep. Yeah, because otherwise you'd kind of freeze while you waited to learn about the past, and then you would fast forward, and that would be very awkward in those applications.
And some video and audio applications do that. They'll actually play the other person's voice faster for a period of time to catch you up.
Right.
Instead of dropping packets and just getting you up to real time.
Yeah, and that can work sometimes. And so, yeah, it's a trade-off, and it's for sure an application level trade-off. And so it was initially, I think, kind of thought in the 70s and 80s maybe that TCP is all you'd ever want. But as more of these more real-time applications came into being, then it became clear, well, we need something else. And if I don't want to use TCP in the model we've talked about so far, I could maybe try to use raw IP, but there's a problem that I'm going to encounter if I try to use raw IP. And what is that?
Well, congestion control for one. You're going to become really greedy on the network and possibly starve out people or yourself.
But I'm a smart application developer. I can solve that. The one that I was worried about is TCP includes these port numbers, which are used to indicate which applications are communicating. And so
the little router in your operating system that we talked about.
Exactly. And so it turns out you need a way to communicate to specific services or applications on a computer without using TCP. And so this is where another protocol came in called UDP, User Datagram Protocol, whose basic purpose was to give you port numbers without the rest of TCP. And so it's a much smaller header. Like TCP's header by default is 20 bytes. I think the UDP header is like 8 bytes. It's quite small. And essentially it's a couple port numbers, and then it has like a checksum because it turns out IP doesn't actually promise that your data is delivered correctly. It just checks the headers as it goes. And so as an application developer, if you want to do your own error correction, your own flow control, your own all the things TCP does, or you just don't need those, then you can use UDP instead.
Yep.
And some applications do this. And even now, some applications that want to be able to get higher performance than TCP promises with its service model will use UDP. And so some web browsers now can use UDP, and I think, is that HTTP 2? I think they use UDP as well, possibly, in order to essentially bypass some of the TCP restrictions.
Yeah, there's a protocol called QUIC.
Yep.
QUIC, Quick UDP Internet Connections, that I don't know if HTTP 2 picks that up, but Google did kind of develop this.
Okay. Yeah, and maybe I'm thinking of HTTP 3. I think QUIC is at least part of one of the HTTP proposed standards in later revisions. I can't remember which one.
Mm-hmm.
So yeah, that's one example, and that's an important one. There is, it turns out, another downside to TCP that motivates some applications to not use it. And that is, remember that initial what's called three-way handshake, where I send the SYN, you send the SYN-ACK, I send an ACK back. Now we get to the communicating about data part. What if I could just send you a message and you could just send me a response and we'd be done? We'd have done that before we even got a TCP session up and running.
So a two-way handshake instead of a three-way.
Yeah, or just, a query and response. And so DNS, the domain name system, which we'll talk about at some point, which is how you take a web URL that has a name of a service and it finds the actual IP address of the server you want to connect to. By default, that'll use UDP because I just say, what's the IP address for this host name? And then I get a response. And I never had to even create a session. I can just ask again if I don't get an answer.
Yeah.
So that's an example. And then other kind of lightweight or ephemeral communications mechanisms will use UDP as well, just because there's so much lower overhead. But the majority of the time, TCP provides that reliable service model, and so that makes it the best choice, and that's what most application protocols use by default.
Yeah, and most applications on most networks really don't need any more speed than what TCP provides because most networks are reliable.
Yeah.
And most applications have all kinds of little hacks to work around some of TCP's warts.
Yep, that's very true.
All right. Well, Shane, we had some explaining to do. We did some explaining.
I think so.
Did we do all the explaining we need to do?
I think we did. I think we covered TCP in fine form and even a little bit of UDP too.
All right. Well, I enjoyed it. Thanks, Shane, as always, for sharing your wisdom and knowledge.
Yeah, you too, Dave.
Until next time, I send you a fin.
All right, Finac.